Welcome, everybody. Thanks so much for coming along today. I know for many of you, you're going to be potentially stuck at home, uh, looking after children, doing all sorts of other things. So the fact that you're able to participate, even though that you're not able to actually fly around the world, I think that's fantastic. Uh, I'm going to be sort of sharing with you some thoughts about microservices, coupling, cohesion, information hiding, and a whole bunch of other ideas. And in some degrees, these are kind of old school computer science ideas, but I think in another very real way, they're kind of really important topics and very important subjects for us to look at. I think we often lose sight of the things that came before because the shiny stuff is way more interesting. And so I'm hopefully going to show you some of the earlier ideas from sort of the area of structured programming that might help you build a better microservice architecture. A very quick bit of background about me. I previously wrote a book about microservices, building microservices. That book was released in early 2015. I'm in the process of working on a second edition. That's at the very early stages. My most recent book, Monolith to Microservices, was released at the end of last year. This is a deep dive on how we take systems and decompose them. I was actually just doing did a 2-day online class. Maybe some of you in the audience came along to that class, in which case there's going to be some overlap. But if you want to know more about the work that I do, see some of the other talks that I've done in the past, you can find lots of information over at my website. But we're here today to talk about microservices, as is quite common for me. That's what I end up doing a lot. And when I talk about microservice architectures, I always try to sort of zero in on the thing that makes them interesting as an architectural choice. And that one of those key characteristics that we're often aiming for with a microservice architecture is this idea of independent deployability. So the idea that I can go to a service, I can make a change to that service and deploy that into a production environment without actually having to change anything else. Now, this is often quite tricky to make work in practice. One of the things that often comes up very early on is, okay, well, that's a great idea. And sure, we can talk about things like zero downtime deployments and all this kind of fun techie stuff, but it often just starts with how do you handle independent deployability when you consider the fact that that microservice is being used by other people? In other words, what about those sort of upstream consumers of your service? When we think about independent deployability, if I'm going to change the account service in this situation, I want to be able to make that change in isolation, make a change to accounts, deploy it into production, release that functionality to my customers, to the users of my software without having to change anything else. So that means in this particular situation, when I redeploy version 2 of the account service, I need to make sure that the customer service, which is upstream, which is an upstream consumer of the service, that still is able to work. So I have to maintain backwards compatibility. If I don't maintain backwards compatibility, when I make a change, I deploy that microservice, I could end up breaking my upstream consumer, which could often have quite catastrophic effects for a system if that causes some kind of cascade of failures. So we've got this idea of a group of functionality which uses another group of functionality, and I want to be able to change some of that functionality independent of other functionality and still make sure that they all work together. This seems like quite a tricky problem to deal with, and it can be, but luckily we have been here before. Namely, we were here before back in the 1960s. Back in the 1960s, much of our computing was done on mainframes. We were operated in a world where we had a small number of very large machines that would look not that dissimilar to this sort of thing, where, just because of how difficult it was to build computers, we didn't have many of them. And that meant most of our software was running on mainframe-based applications. As the mainframes became more powerful, as advances in computer science allowed us to build more complicated and larger programs, we started realizing that we needed ways to organize those programs to make them more manageable. Some of you today might rail against your sort of single process monolithic applications becoming a big ball of mud. Often that's just the case of not finding ways to structure that code in the right way. So a lot of work was done back in the 1960s and into the 1970s, looking at how do we structure a program in order to make larger programs easier to work with. One of the core ideas that came out of this space at the time is the idea of having software broken down into modules. The idea here is that a module can be worked on independently. One module can expose functionality that can be used by a different module. These modules allow for a degree of independent working. If I had lots of different developers or even lots of different teams, I could have some developers working on module A, some other developers working on module B, and so on and so forth. Great, that works pretty well. These modules also would allow some degree of reuse. Depending on the nature of the technology that you were using, you may be able to take, say, module C and reuse that in a different program. And this would give us reusability of functionality across different programs. Now, modules as a concept have been around for a very long time, but in a lot of our modern programming languages, the concept and importance of modules has been reduced somewhat. At one level, we have capabilities in our programming languages like namespaces or packages in Java. These are ways where you can group code together and say, okay, this code is hidden inside this module. This code is available to another module, another package elsewhere. We could then take those packages, those namespaces, and sort of bundle them together in a NuGet package, an NPM, a jar file that then gives us the ability to reuse those modules between different programs. So we have all of the same building blocks that allow us to create modules in our modern programs, but we often don't really use them in the same way as we used to think about structured programming. Often the way we kind of organize our code into namespaces and packages is way too much of just an afterthought. And it's kind of just an arbitrary categorization rather than thinking about grouping our code into isolated modules that can be easily changed independently from each other. Nowadays, of course, we operate in the world of microservices, and the microservice world has changed. Microservices, we can think of microservices now as collections of functionality hosted on a networked endpoint. Fundamentally, it's a module, though. A microservice individually is a collection of functionality that now communicates over networks with other modules. These modules now just happen to run on different computers. Whereas before they were typically all run on the same machine, now these modules run on different computers. The communication between those modules is done via network calls, some kind of network protocol typically. It could be a synchronous or an asynchronous protocol. It doesn't really matter too much for the sake of this conversation. The fact that we run these things now as separate processes, typically on separate computers, means that we have a much easier time of deploying these things. We can deploy them now independently. Whereas typically for modular-based software before, we would think about including a module into a program as a static linking activity. I would package all of those modules together and deploy them as one big thing. Whereas now we can kind of think of our modular architecture as being modules that can be worked on independently, yes, but also deployed independently. And that's kind of the shift. And that's really come about because we've got more computers. In the 90s, we saw a shift from larger, very expensive mainframe-based systems over to much more cost-effective server-based infrastructure. So now we had a large amount of smaller machines rather than a small amount of large machines. And you can see all the work done around things like service-oriented architecture that followed as an attempt to come to grips with the new economies of computing. How do we build applications that make use of the fact that we now have a lot more computers? But I think often in all that scramble, we've sort of lost sight of a lot of the lessons we learn about building modular software. And I do think that when done right, microservices are just a form of modular architecture. So this is saying weird. Let's talk about some of the background to all of this. Let's talk about information hiding. So information hiding was a concept developed by David Parnass back in 1971. And David Parnass was doing some research looking into, well, if we've got these ideas of modules, what's the right way to find a boundary for a module? How to ensure that one module can be worked on independently without causing problems elsewhere? So his work, published in 1971, really zoned in on this idea of information hiding. And we'll come back to this concept of information hiding, but basically it entails sort of hiding as much stuff as possible inside the service boundary. The idea here is that if information that's hidden away can be changed freely, any information that a module exposes to another module is something that effectively becomes part of the contract that that module exposes to the outside world. And so if we hide as much as possible, we can change lots of things without worrying about having a cascading effect. There's actually a really nice piece work done by Adrian Collier. Adrian Collier writes a really good blog called The Morning Paper, where he looks back over sort of computer research papers and summarizes them for mortal people. And he actually took a look back at David Parnas's work in this area. And he said, well, what would happen if we just took the word module and replaced it with the word microservice? Would these papers still make sense? And, indeed, he found that, certainly when looking into the ideas of information hiding and the other work that David Parnas did in the area of sort of modular decomposition, that actually these ideas do stack up. And it's actually quite a nice moment in one of these blogs where David Parnas himself starts leaving comments on the blog post talking about how his own current thoughts about the subject. So coming back to information hiding, so you may well want to go read those Adrian Collier papers because they're really interesting. But going back to this idea of information hiding, the idea really at one level is quite simple. So here I've got some sort of microservice here, and I've got internal implementation detail. I've got some external consumer that's going to make use of the functionality that my account service in this example exposes. And that shipping service here can reach right in and gain access to some of my internal implementation details. And that then leads to a bit of a problem, because if I change some of that internal implementation detail, then that's going to break the consumer. So I might change some innocent piece of internal detail that an external party needed. The contract, therefore, with my upstream party has been violated, and I've kind of lost the ability to do independent deployability. Because if I deploy this account service in this state, it's going to break an existing consumer. With information hiding, the idea here is that you're being quite explicit about what information you expose, so what functionality you expose. And that is, you're being explicit not only to the person using your service, but also to the person developing that service. So if you can clearly differentiate between functionality which is hidden from the outside world and functionality which is shared with the outside world, you make it very easy for a developer to reason about what information can be easily changed. The shipping service here only has access to that shared information. If I change anything there, I am aware that I may well end up breaking that upstream consumer. But anything in that hidden space, that's stuff that I should be free to change without worrying. And so when you're building microservices, one of the earliest pieces of advice I can give you is share as little as possible. Hide everything you can. And if anything that is part of the external contract that you're exposing with an outside party, that should be made very, very explicit to the developer working or the developers working on that service. Sometimes we do things that make these, what we share, not very explicit at all. So here's an example of, and this can introduce areas of accidental breakages, where you'll be making an innocent change to a piece of code without realizing that that has an effect on the public contract. So quite a common pattern I see is someone taking, say, a class definition like this and mapping it to some kind of JSON payload. And that's a JSON payload that's going to be, say, exposed over a network boundary and used by another service. So in this example here, we expose a customer from this service. We take that customer object, run it through some kind of JSON serializer that's just going to walk the fields of a given object and convert that into the mapping, to the JSON mapped version of that. And there are goodness knows how many libraries out there that will do something like this for very different languages and take just data structures and map them to JSON quite straightforwardly. Now, if I'm working as a developer, I look at that customer class and I think, hang on a minute, we're storing an age. Why would we store the age of a customer? That seems a bit odd. It seems to make much more sense that we actually store, say, a date of birth. So I might change that to store a date of birth. Unbeknownst to me, though, that customer object is actually being serialized and exposed over my network boundary. So if you now serialize that object again, the age field has vanished. It's now been replaced with a date of birth field. Now, if I wasn't aware that that customer object was being serialized, I could make a change to that customer object very easily that breaks external parties. And I see this happen a surprising amount. If you're going to do something like automatically mapping from a piece of code or a data structure into something like a JSON structure, I would suggest making it very explicit to the developer. Make your heavy use of annotations, maybe explicitly mark fields that will be serialized and make it an opt-in. And then at least there'll be a visual cue to the developer that there's something going on here that they need to be aware of. You might even want to consider doing something like creating a data transfer object. This is a pattern that Martin Fowler sort of captured in his book, Enterprise Application Architecture. And it's the basic idea of the data transfer object to say is that I've got my internal representation of something, but I might have quite a different external representation. So I might have my customer that I use inside my service boundary, and see here I've made the decision to change that customer field to be a date of birth rather than the age. But I recognize I still have to expose the age to the outside world because that's what the people externally expect. And so I basically create a data transfer object representing that customer, and I recognize that that data transfer object is what will effectively be serialized and sent over the wire. So that can give you some separation between internal representation and external representation. And so as a developer, I'm going to have to explicitly go and change my customer DTO to change that external representation. And that's something that's going to be a very conscious thing, right? You put it in a separate package if you want to. In some projects like this, I would even put watches on DTO objects to see if they're being changed in ways that are backwards compatible or backwards incompatible. So that's kind of really important, right? So being very explicit from a developer point of view about what can and can't change. Going back to some other work done by David Parnas, he talks about this idea that when we think about modules, the connections between them are the assumptions that modules make about each other. So in other words, a call that one module makes to another, basically one module A that talks to module B, module A has assumptions of how module B is going to behave. The connections are effectively the calls that we would make in, say, a microservice architecture implicitly imply it's definitely a redundancy, but they imply we have an assumption about how that microservice is going to behave. With information hiding, we're reducing how many assumptions that we have to make about another microservice or another module generically. The problem often is that these connections, these assumptions we make about the modules or the microservices we call, are often purely captured in an implicit way. We are not explicit about that. And I'm a big fan, where possible, of being explicit about the assumptions you're making where possible. If you are explicit about about what module B thinks module D should do, for example, then it becomes much easier for you to reason about what things can change safely and what things cannot. So what kind of tools have we got here that can help us in terms of being explicit about what we expect of another module? Well, this is actually an area where schemas can help greatly. And I think it's a bit unfortunate that sort of in the time since the SOA, or sort of the way we're implementing service-oriented architectures, with things like SOAP and WSDL, when that fell out of favor, we seem to have ditched a lot of other ideas in that space at the same time. WSDL, which is the schema format for SOAP, is not much fun to work with, but we seem to have got rid of the idea of any schema rather than just reflecting on the fact that maybe that schema wasn't great. I actually think schemas are very useful because they allow you to make an explicit definition of what a microservice exposes. That again becomes an explicit representation for your developer working on that microservice as to what they need to maintain backwards compatibility. It is also an explicit representation of the assumptions that an upstream microservice has of you. I know loads of you are probably sending JSON over HTTP. That's probably the most common form of inter-process communication, is some style of JSON over HTTP communication. Now, I personally am not a big fan of JSON for general service-to-service communication. I think it's fine for a browser, but I think it's got a lot to be desired for communication within a services estate. And JSON typically is used without a schema, but you do have the option of using a schema with JSON. There's a thing called JSON schema, which, although it hasn't got a final version, has a perfectly usable draft, and that's something that can be used today. So you can still carry on using your JSON over HTTP, but you could also now optionally have a schema that says, and here is how I'm going to expose my data. And I think that's very useful, very, very useful. Schemas, one done well, can also allow you to generate client-side code that is able to read those payloads automatically. So we kind of get this benefit of being explicit about what our microservice or our module exposes, but we also get the ability to generate code to read those endpoints. A great example of that would be something like the Google protobuffer specification. So this is an open source serialization mechanism. It's also used inside gRPC. And so here on the right hand side here, I see a very, very simple protocol specification. This is exposing kind of the different types that an endpoint is exposing. And so it's very easy for an external party to now generate code against that. And Google proto buffers allow for a high degree of interoperability between different languages. The serialization form itself is also significantly more efficient than JSON in terms of the time taken to serialize, deserialize, and transmit. So there may be some other wins for you there if you're looking for to eke other efficiencies out of your inter-process communication. One of the nice things around a schema is that you have, theoretically at least, the ability to compare different versions of a schema and reason about whether or not the changes made from one version to another are backwards compatible. And for something like protocol buffers, we actually have a program and a tool chain to do that. There's a tool called ProtoLock, which allows you to compare and contrast two different schemas and say, are they matching? So this could be a great thing for your service. If your service exposed some sort of proto buffer endpoint, you could easily put this into your build. You make a change to that protocol specification, and the build says, yes, that's backwards compatible. The build passes, or no, that won't be backwards compatible, and I'm going to fail the build. And then at least you get some fast feedback. Obviously, schemas aren't the only way forward for this. Testing also is a huge part of maintaining and making sure you have some degree of backwards compatibility. And again, good testing can really help in terms of independent deployability. What I will say is if you don't have schemas, you're likely going to have to do more testing to get the same degree of confidence. So I think schemas and testing can complement each other very, very well in the same way that static typing and testing can still go together hand in hand. So we've talked a bit about information hiding, and it is a super, super important concept. And if there's only one thing you take away from the presentation today, should be, I should hide as much as possible. All right, information hiding is super, super useful. But there's other ideas that we can look at as well that come from sort of the wider field of structured programming. These books are actually surprisingly hard to get hold of nowadays. I managed to get a copy of the book on the right. The book on the left goes for about 80 quid at the moment and takes a long time to arrive. So I have to say I've relied on online versions of this book, but you can find it, I think, over at archive.org as part of their lending process. Anyway, these are some of the seminal books, certainly the structured design book by Jordan and Constantine on the left, which outlined a whole lot of the concepts around how we think about structured programming, and they gave us a whole bunch of terms that we kind of now take for granted. Two of those terms that we now take for granted are coupling and cohesion. We talk about these ideas quite a bit, especially in the context of object-oriented programming, and often as well in the context of services-based programming. We don't necessarily, though, always have a good understanding about what these terms mean, but we tend to know what the desirable types of these things are. So we talk about wanting low coupling and strong cohesion. So that's what we tend to say. We want these things, and we'll talk about why just in a moment. So let's talk about what these terms mean. Well, cohesion is the kind of idea that, well, there's different definitions. The one I like the best, and I know where I originally heard this from, is the code that changes together stays together. So in other words, if I've got all my invoicing functionality that I've got to change, I would like to be able to change that in one place, keep that code in one place, rather than having to go to lots of parts of my code base to make that change happen. By having all that functionality in one place, makes it much easier for me to say, remove duplication, create abstractions, all that good stuff. But it also reduces the amount of work required to make changes. And we often might see the opposite of this. We might see examples of weak cohesion. And we've probably all worked on systems and maybe distributed systems where you have to sort of go to like 5, 10, 15 20 different places in your architecture in order to make a change to that software. You know, the invoicing functionality is spread all over, payrolls in about 5 different places. And we have to go and make changes in like 2, 3, 4, 5, 6 different services just to roll out a simple feature. And then when we have architectures that have this sort of weak cohesion, that can often lead to a much higher maintenance costs as well. With a services architecture, that can lead us into the world of things like the distributed monolith. Now, cohesion kind of goes hand in hand with coupling, and coupling is the degree to which changing one module requires a change in another module. If my cohesion is weak, I'll have to go and change lots of things. If I want to change that functionality, I've got to go and change it in lots of places. That leads to coupling because I'm having to change all of those things together. So as we have weaker cohesion, we tend to have tighter coupling. What we want, of course, is we want looser, lower coupling. So as we reduce coupling, we will tend to find that our cohesion improves. So there's a vicious or virtuous relationship there. And this actually gives rise to something that's known as Constantine's law, which states that if a structure is stable, if the cohesion is strong and the coupling is low. Now, remember what we want for our microservices? We want independent deployability. To have independent deployability, we need a stable interface. So with that in mind, we want microservices which have a strong degree of cohesion and have loose or low coupling with other microservices. And based on these ideas, that should give us a stable microservice boundary that makes it easy for us to develop independently. So if you want independent deployability, information hiding is really, really important, as are having strong cohesion and loose coupling. Now, coupling is a bit more of a nuanced concept, and it comes up in lots of different forms. So I'm going to take you through a few different forms. And some of these are terms taken directly from structured programming. Some of them I've changed a little bit. I'm trying to work on kind of a model to describe the different forms of coupling in the context of microservices. So this is far from a finished piece of work. But we're going to look, I think we'll actually skip over tramp coupling because it's a bit of a niche one. But we're going to take a look at domain coupling, common coupling, and content coupling, and look at how these different forms of coupling would manifest themselves in a distributed system, and maybe talk a bit about how we could fix those problems. In general, when we think about these different forms of coupling, we're looking to find looser forms of coupling. So domain coupling over here on the left is a fairly loose form of coupling. We get over to something like content coupling, which is also known as pathological coupling. This is where we're getting to really, really tight forms of coupling. So in general, when you find a form of coupling, you're going to think, well, can I kind of replace this with a different form of coupling that might be better for me, that's looser, that allows me more ability to change things independently? We'll start off with the kind of the easiest one, which is domain coupling. And so here's domain coupling. So I've got a service here over on the left called the order processor. And this is involved in some kind of process to reserve stock and take payments, right? So this looks like a sort of orchestrated process to handle, on some online e-commerce company maybe. So I'm talking to a warehouse. I've probably got some physical inventory going on. I'm taking money. It's the kinds of things you could imagine an e-commerce company would need. So the order processor needs to use functionality in the warehouse service. The warehouse service here exposes the functionality to allow me to reserve stock, and the payment service allows me to use the functionality to take payments, which is kind of what you would expect from a payment service. The order process here is said to have domain coupling with the warehouse and with the payment. The order processor needs to make use of the domain exposed by the warehouse and the domain exposed by the payment service. If the warehouse changes its functionality, changes that part of the domain, changes how stock is managed, for example, in such a way that it impacts that contract, the order processor would also need to change. Having some degree of domain coupling in a microservice architecture is pretty much inescapable. What we've done with our microservice architecture is broken things down into, this functionality is using functionality in this microservice over here. We do need to collaborate with other microservices from time to time to get things done. So this is to some extent unescapable, but we can also still take attempts to limit it. So here the order processor has a degree of domain coupling to both warehouse and payment. It's therefore vulnerable if the warehouse or payment make changes that change their contract. But there is no domain coupling between the warehouse and the payment service. They don't talk to each other. There's no communication between them whatsoever. So a change to payment is never going to affect warehouse directly. And so if you can reduce how many services that you have domain coupling on, you're likely going to make it easier to evolve your services in isolation. One of the sort of smells you can look for, one of the potential problems you can look for, are microservices that have lots of outbound domain coupling. Something like an order processor is often the kind of service that could well end up talking to about 5, 10, 15, 20 different microservices. So it will have a high degree of domain coupling to lots of other outbound services. And in that situation, you're always worried that it's doing too much. That could sometimes point to a centralization of logic, but it also means you've got a microservice which is much more vulnerable to other changes that might be made in the system. you'll typically find that microservices that have a high degree of domain coupling will often also have a high degree of volatility, the extent to which it has to change because of these other changes that may be happening in the system. So you always want to be keeping an eye on those. Whenever you see a microservice that depends on loads of other things, take a good hard look at it. And you know, in the same way that you would say look at a God class in a code base which might be doing way too many things, and think, is there a way we could maybe split this apart? The next form of coupling we're going to look at is common coupling. So common coupling is where we have multiple microservices that are all depending on some externally defined sort of data source. So in this example here, I've got stock levels. So these stock levels could be held in like a Redis cache, or, you know, it could be a database table, or it could be, say, a file location. And the warehouse needs to read and write from those stock levels. And the order processor needs to check those stock levels. And we've also got our forecasting service over here, which needs to also do things with those stock levels to check how much, you know, stock we're selling and maybe make decisions about what we should order. So a common coupling describes a situation where, like, you have a microservice which depends on an externally defined data set. The issue, of course, here is that if we change that stock level service, that stock levels data source, we're going to potentially impact multiple different microservices here. And often with data sources like this, we're allowing direct data access. Another example that could be similar to this would be something like a data warehouse. You know, if you're having all these services having to push data into a centralized data warehouse, that's arguably a form of common coupling, although typically that is mitigated by the fact that, you know, you're typically doing read-only access to those data warehouses, where something like stock levels, where I've got read and write behavior, we're a bit more concerned about something like this. The issue, of course, here is that any changes to stock levels ends up having quite a significant impact on our system. And in fact, when you tend to find common coupling, you tend to find like some sort of data store in the middle of it that's just never going to be able to change in any way, shape, or form, because the impacts of that are too great. So manageable in some situations, but you again really do want to limit this where appropriate. And actually being maybe more selective in what data is stored or managed in this way would be useful. An example of common coupling that you might find within a program would be things like shared memory locations, so shared mutable state. So whenever you have mutable state that's shared by multiple different bits of code or different processes, we have a real issue there, because effectively we can end up with situations where you're effectively doing communication via these shared memory locations, which can get really nasty. So even within common coupling, there are some forms that are worse than others. The last form of coupling we're going to look at is something called content coupling. And content coupling is the worst form of coupling that you'll see. It's also, unfortunately, something I still see far too often. So here I've got an order service, and that order service manages the life cycle of a given order. And very simplistically here, we've sort of modeled that as it basically uses a table inside its own database where it can manage the state of a row. So when I make a change to an order, I'm going to update that row. Okay, so pretty straightforward approach. One of the ways in which we ensure that microservices can be independently deployable is we look to also isolate data. We want microservices to own their own data management. So that means that other microservices, if they want to make a change in state, have to come to that service and say, please, can I make a change in this state? So here I've got the order processor, which is coming to the order service and saying, could you update this order, please? So the way this would work is an order processor would send some form of request over whatever protocol it sees fit. And it might say, can you please mark this order into a shipped state? Our order service would take a look at its local data and say, well, based on the current state of this order, based on the request being made, that yes, this is an allowable state transition, and I will now move it into a shipped state. Or no, it's not, and it might reject that. The idea being here that the order actually manages the set of allowable state transitions around a piece of data. And so that kind of can encapsulate the logic and state of this service. Of course, we could do something fancy like run an event source system in here if we wanted to, but let's keep things simple with tables. And so the nice thing about this is that we have a single source of truth for where we get our order information. It is the order service, and we go to the order service to request the information we want. By going to an explicit service interface to ask for information about an order, we actually ensure that the microservice, the order microservice, exposes only what limited data it needs to. It can hide a lot of the detail in that database that no one else needs to know about. There might be other things it needs to track to do its job. No one else in the outside world should know or care about that. But oh no, along comes the warehouse service. And the warehouse service, for reasons we don't fully understand, has direct access to the order services database. So it can now directly read order state from that database. It is also able to make changes to that data state, maybe by saying, okay, this order is now in a picking state. So picking is the process by which people go around a warehouse, pick things up and put them into boxes. At this point, we've completely bypassed information hiding. We are no longer available to decide about what information is hidden from the outside world. Everything in our database is effectively now shared. It's completely unclear to us now when working on that order service as to what parts of our database can be changed easily. We may even have challenges here about doing things like adding new database constraints, because we know or are aware that we've got this other warehouse service out there that has this connection straight into our database. We mentioned before that the connections between modules also kind of define the assumptions that modules have of other modules. Well, here the warehouse has a connection to our database. So the warehouse clearly has expectations, it has assumptions about what functionality we should be providing to that warehouse, but it is completely implicit to us. How can we be explicit about what we think the warehouse needs? The only thing we've got to go on maybe is the structure of our database, and that's not a great schema in this context. The other problem with this model is that we might have logic and code inside the order service that says these things are allowable state transitions. This is the logic about how this object, this entity is allowed to change. These are the set of allowable state transitions that you can have. But if we allow people to bypass that logic and go direct to the database, either they've got a duplicate implementation of that same functionality, in which case we're lacking cohesion, or they've got a different implementation, in which case we're in the world where we might have inconsistent data, our data being updated in inconsistent ways. There's a reason that this form of coupling is called pathological coupling. When you reach directly into another service's implementation like this, and reaching directly into another service's database is the worst form of that. This is a very, very tight form of coupling. And the right fix here would be to get the warehouse to, rather than going straight to the database, would actually be go to maybe an interface exposed by the order. That could be a REST-based API or an evented endpoint or some other exposed or queue or something else. Don't bypass the information hiding and go to a well-defined service interface, and you'll be better off. So just to summarize, there are different forms of coupling out there. When you encounter these different forms of coupling, what you're going to try and do is sort of drag them from the right to the left. If we make our coupling, if we sort of decrease the amount of coupling we have, we are going to make it much easier for us to make our software independently deployable. So when you encounter these ideas, when you encounter, say, content coupling or common coupling, think, can I get that functionality and change it in such a way that now maybe it's using domain coupling, or perhaps even remove the relationship altogether? So just in summary, information hiding is super, super important, okay? It's vital that you kind of hide as much as possible. Anything you expose, when you choose to expose some information, this could be a piece of data, this could be a method, expose that in a way that makes what you're exposing very explicit. Strongly consider the use of an explicit contract to say, this is what I'm exposing. Having an explicit declaration about what you expose is going to be useful for clients that are using your service. It's also going to be super useful for people who are developing on that service, because they understand what things can be safely changed and what things cannot. So whatever mechanism makes sense for you, look at maybe look at DTOs if that's going to work for you. Look at something like explicit schemas, annotate any classes that are used in serialization. All of these are things that can help. Tests can also be part of that, but I think you can do more than just adding tests to this sort of thing. Some coupling, when you get into it, is worse than others. Common coupling and that sort of pathological content coupling is really, really bad. So if we can maybe shift that more towards domain coupling, we'll make our coupling looser. We therefore make independent deployability much easier as well. Along the lines, we'll actually end up making our systems have a higher degree of cohesion, which in turn should actually reduce our maintenance costs, which is a lot of what this is all about. But information hiding, low coupling, and strong cohesion, all of these ideas build up to giving you that idea of independent deployability. I hope this was of use. I didn't want to keep you too long. I've got a lot more information over at my website, including information about my latest book and the services I offer. And you can find lots of that stuff over there. I will get the slides for this talk uploaded there shortly. But we do have a little bit of time left for questions, I believe. So I think I will just exit the sharing from this. So let's stop sharing and take a look to see if we've got any question. Okay, so let's take a quick look at this. So we've had a question here from Janice Lounge. So Janice says, and I am going to apologize up front if I get your names wrong. So I've heard talk about high cohesion, low cohesion, not strong, weak. Is there a semantic difference or just different wording? The strong, weak cohesion is the terms that were originally used in structured programming. And so because I'm trying to sort of unify that work a little bit, I'm trying to use the original terms here, but you can consider them as being the same concepts. So you can think of them as a spectrum. So high cohesion, you can consider to be the same as strong cohesion. Low cohesion, the same as weak cohesion. I'm sort of trying to go back to the original terms at the moment, purely because I'm spending so much time reading books from the 1970s that switching my brain patterns is proving to be difficult. So you've mentioned you're not really a fan of JSON as the communication between services. What would you recommend as an alternative and why? Well, so why am I not a big fan of JSON? Well, firstly, it doesn't require a schema. Yes, you've got JSON schema, that helps, but it's not, the fact that most people don't use it with JSON is a problem. The second thing is, what is JSON being compared to? People picked up JSON largely because they thought it was less verbose than XML. Now, we can put aside the fact that actually once you send it over the wire and compress it, it's not much smaller than XML. Secondly, why do you care about how verbose it looks? It's not there for a human being to read, it's there for a computer to read. So by all means, use JSON for configuration files, but by and large, we really like to pick serialization protocols, or sometimes encodings, as some people refer to them, as things that are easy for a computer to create and another computer to read. And JSON is all right for that, but there are other forms that are much more efficient. So protocol buffers, for example, are significantly more efficient to serialize, deserialize, and read. Also, something like protocol buffers has significantly better support built in for enabling you to make reasoned decisions about making payloads backwards compatible. By all means, use JSON for human readable things if you want to, or although I think YAML is slightly better for human readable configuration stuff, but I would tend to restrict the use of JSON to communication to kind of your front end devices. Better serialization mechanisms that I'd be more interested in using, protocol buffers. I'd also look at Avro. Avro effectively is sort of a JSON based protocol, but actually has explicit schemas and has some really nice, interesting support for almost like interpreting different payloads using different versions of schemas. So I could actually write effectively something that can interpret payloads from multiple different versions of the same Avro schema, almost using sort of binding to payloads a bit like I'd sort of handle a dynamic type. So have a look at Avro as a serialization format, and that's quite heavily used in messaging or protocol buffers. And by the way, there's no reason why you couldn't theoretically send those things over a HTTP or REST-based interface. The other thing you could potentially look at is maybe look at something like Open API specification. So this is not replacing the serialization format, but is at least giving you a way to define a schema for a REST-based interface that would be making use of JSON as a serialization format. So the question is one last question here, and we'll take a break. The way you describe it, it seems that content coupling and common coupling are similar. Is the difference the persistence mechanism? Content coupling is about a shared database, while common coupling is about shared state in a more volatile fashion. Not quite. The distinction is a bit kind of less well defined than I would like. So common coupling is where you've got content coupling. So common coupling is where you have a common externally defined data source that multiple people access. So you say this thing, loads of people can access, go at it. So that would be your traditional shared database. Everyone can go access that. So content coupling, on the other hand, is where you reach inside of somebody else's implementation detail. So there is a subtle difference. So when you with common coupling, you typically say this is a common data source. everyone could do what they want with that common data source. It is a free-for-all. Um, Content coupling is by reaching into somebody else's implementation detail. So that's the distinction. I'm still working through those models, trying to come up with some better distinctions. It's a weird thing that a lot of those distinctions are much more stark when we look at it in code form than we look at it in services form. So I'm still working through those models. The key thing is they're both not great, but reaching inside another service's implementation into its database is worse, often because we're bypassing a lot of logic around how that data should be managed. But I can understand the overlap there. All right, we are at time. Thank you so much for coming along and asking questions. So I've seen some familiar faces on the attendee list as well. So thanks for coming on to one of my talks again. If you want to know more about anything I do, you can pop over to so you can pop over to my website, which is just samnewman.io. You can also find me over at Sam Newman. If there are any questions I didn't get to, I am going to be on this Slack channel, and I'll be hanging around there for the rest of the day. So thank you so much for your time.